Welcome to LINNC Paris 2022, and we have the honor to be discussing with Jay Mocco, who is a professor at Mount Sinai in New York.
That is correct.
And you're going to be talking about a subject that's quite interesting because we haven't discussed it yet. It's transvascular brain-computer interface.
That's correct.
I'd like to expand on that, please.
Absolutely. It's an incredibly exciting direction for neurointervention as a whole, and really, in some ways, for humanity as a whole. I have the opportunity to work with a company that's developing a transvascular brain-computer interface. So much like we put in coils to treat aneurysms, or put in flow diverters, or go in to take a clot out for a stroke, the blood vessels provide us access to all kinds of aspects of the brain. It's not that long ago that in cardiology, they use blood vessels to rewire the heart, right? To ablate the heart, to put in pacemakers and defibrillators. There's no reason why we can't do that for the brain. And so we're actually, in the next month, going to be doing the first case in the United States. There have been 4 cases completed in Australia of going through the blood vessels and putting in a stent electrode in the sagittal sinus that can read the motor cortex. So for a patient who's suffering from paralysis, who has ALS, who has spinal cord injury, or any number of stroke, that has a disconnect from a functioning motor cortex to the rest of their body, this can read that signal, be completely under the skin, transmit through the skin, no need to have wires going into your head or anything like that, and send via Bluetooth a message to the computer so that paralyzed person can turn on their computer, turn it off, send a WhatsApp, communicate with people. We have videos of the people who've had it turning lights on in their house and other things. It's an incredible game changer for those types of patients.
I imagine also it gives you information. Could it give you information, for instance, during an intervention at the state of the brain if the person can't respond?
It absolutely could. So it reads the brain electrical signal. So certainly you could have it during an intervention, just like people put EEGs on the outside of the head. Right. Additionally, you could have a long-term device implanted so that you can sense if a seizure is going to start and have a closed-loop feedback to stimulate the brain, essentially to defibrillate the seizure.
Yeah, essentially like a pacemaker.
Exactly. Now there's a technology called NeuroPace that's been doing this, but it requires a very large craniotomy, and it's been difficult to get people to embrace it. But can you imagine if you only have to go in for an outpatient transvascular procedure, and then you could potentially have a defibrillator to stop your seizures?
Well, that's incredible for epilepsy, but I imagine that there are also a tremendous amount of uses afterwards, especially for reading the brain. Where do you see this advancing afterwards? I mean, what does this open for you?
I mean, I think the doors are nearly limitless. I think obviously the first step is to return function to people that have lost that ability. You know, there are many paralyzed individuals that even a little bit of increased function to interact with their society and with the environment and through electronic technology.
And communicating.
Correct.
Simply communicating.
Correct. Imagine trying to work your phone, that so much of our lives go through, if you can't use your hands. Huh. You can't. It's too difficult. Open to close, to scan through the choices, to move. But if you can just work your phone, your level of quality of life would go through the roof.
Well, this is very exciting. We look forward to speaking with you about this the next time that you're at LINNC. So thank you for joining us.
Thank you.